Hello all. In this lecture we will discuss the canonical form of the hyperbolic equations. The theorem says that suppose that equation 3.1 is hyperbolic. That means the second order equation which is in the standard form is hyperbolic in a domain D. Then there exists a coordinate system theta eta in which the equation has the canonical form W theta eta plus L1 of W is equal to G of theta eta where W of theta eta is equal to U of X in theta eta comma Y of theta eta, and L1 is the first order linear differential operator. G is a function which depends upon the given equation. Okay, so we have to prove that there exists such a coordinate system theta and eta in which the equation is more in more simpler form, that is it contains W of theta eta only the one second order term, that means only one second order term. So in the transformed, we have already proved that in the lemma, the last lecture, by a lemma we have proved that the type of the equation remains unchanged when we transform the equation into another coordinate system by a non-singular coordination, non-singular transformation. So, using that, we can prove this. There exists some coordinate system theta and eta in which the given equation, hyperbolic equation, has a more simpler form. That is, W theta eta plus L1 of W is equal to G of theta eta. So for proving this without loss of generality, we may assume that since this is, we have to prove for second order equations, we assume that at least one of the coefficients of the second order terms A, B of A, B, C, at least one of them is non-zero. And more conveniently, we take as A of xy as not equal to 0 for all x comma y in the domain D. We need to find two functions here. We need to find two functions. We need to find two functions. What? Theta and eta, such that theta is equal to theta of xy and eta is equal to eta of xy, such that what we have to prove, the canonical form is W theta eta plus terms containing that of L1 of W, that means first order terms, first order equation in operator in W, which is equal to again a function of theta and eta. So all other terms, that means theta term and eta terms are absent. So we know when we transform the equation into another coordinate system, that is in theta eta, the transformed equation will be is of the form. We have already written the transformed equations form by that lemma as A W theta theta plus 2B W theta eta plus C W eta eta plus D W theta plus EW eta plus FW equal to G, or in the simpler form it is AW theta theta plus 2B W theta eta plus C into W eta eta, the second order terms, plus we can write it as L1 of W is equal to G. Let this be equation number 2. Okay, so this is the transformed equation. Then we need to prove that we need to find two functions theta and eta in which the transformed equation has only these terms plus L1 of W. That means the coefficients A and C must be equal to 0. So we need to find eta and two functions eta and theta such that A of theta eta is equal to A theta, we know what is A, capital A stands for A theta x square plus 2b theta x theta y plus c theta y square. This must be equal to 0, and the second coefficient c of theta eta is equal to A into c eta x square plus 2b eta x eta y plus c eta y square is must be equal to 0. So we need to find such a transformation in which A and both A and C are 0. Okay, put this as equation number 3 and 4. Equation number 3 is the equation for theta, and equation 4 is the 4 is for eta. But the equations that was obtained for eta is actually the same as that for theta. Therefore, we need to solve only one equation. So let us consider, without loss of generality, we may consider equation number 3. Now equation number 3, when we look at equation number 3, it is a second order equation. Equation which is not a quasi-linear, but it is not quasi-linear, but it has a quadratic form or quadratic structure form in theta, and it is possible to write quadratic form theta. Mm, it is possible to write as a product of two linear terms, and this equation can be written as a product of two linear terms. First of all, we divide and multiply by a throughout the equation, so we will get this expression. Then we try to split the 2b of the second term as a square theta x square plus a into, in bracket, instead of 2b we can write it as b plus b, and plus b plus root of b square minus ac. We can write it as b plus root of b square minus ac plus b minus root of b square minus ac. Theta x theta y plus ac, we can write it as b square minus ac into theta y square is equal to 0. Now this we can write it as a square theta x square that is a square theta x square plus a into b plus root of b square minus ac theta x plus b minus root of b square minus ac into theta y plus b plus root of b square minus ac theta x into b minus root of b square minus ac into theta y equal to 0. Okay, so this again we can write it as a theta x plus b plus root of b square minus ac theta y into a theta x plus b minus root of b square minus ac theta y equal to 0. So now we have written this as a product of two factors is equal to 0. And solving each factor we will get the required function theta and eta. So therefore we need to solve the following two linear equations. Therefore we need to solve the following linear equations. Linear equations. Number one, a theta x plus b plus root of b square minus ac into theta y equal to 0, or a theta x plus b minus root of b square minus ac theta y equal to 0. And let this be equation number 6. So in order to get a non-singular transformation, non-singular transformation theta of xy, eta of xy, we choose theta to be a solution of we choose theta to be a solution of equation number 5, be a solution of 5, and eta to be a solution of 6. So first let us consider equation number 5, that is equation number 5 is a theta x plus b plus root of b square minus ac theta y is equal to 0, which is a first order quasi-linear equation. Quasi-linear equation. Therefore, the characteristic equations are characteristic equations are dx by dt is equal to a, dy by dt equal to b plus root of b square minus ac, and d theta by dt is equal to 0. These are the characteristic equations. Now taking the last one, d theta by dt is equal to 0. D theta by dt equal to 0 implies theta is a constant. Theta is equal to a constant on each characteristic on each characteristic. The characteristics are solutions of the equation. Now the characteristics are the solutions of the equation dy by dx is equal to b plus root of b square minus ac by a. And similarly the function eta can be obtained by solving the characteristic dy by dx is equal to b minus root of b square minus ac by a. And let this be equation number 7 and 8. Now the solutions of equation number 7 and 8, by solving which we will get the functions. Okay, these equations of the characteristics 7 and 8 are called the families of the characteristics of the equation LU equal to G. Families of the characteristics LU equal to G. Okay, from this it is clear that mm, such a transformation exists, such as eta and eta are possible because by solving these equations, equation number 7 and 8, uh, we will find that this will work. That means by solving these equations, we will get two solutions which are independent. So this proves that such functions theta and eta must exist. Okay. So we have proved the first theorem, that is the canonical decomposition, canonical form of parabolic equations. Parabolic equation means it is a second order equation. It's a second order equation.